Hello, and thanks for using TickBoom. A student has sent through this complex numbers question, which reads, W is the complex root of z to the 6 minus 1 equals 0 with the smallest positive argument. Part A says to prove that w squared, w to the 4, and w to the 5 are the roots of z to the 4 plus z squared plus 1 equals 0. And then part B says find the quadratic equation whose roots are alpha and beta, where alpha is w plus w to the 5 and beta is w plus w to the 4. It's a little bit cut off in the screenshot, but you can kind of infer that it is going to be w to the 4, and that becomes a bit more clear once you've worked through part A. Now this is a classic roots of unity question. So we know that z to the 6 minus 1 will have 6 complex roots. Part A kind of tells us that there's this alternative z to the 4 plus z squared plus 1, which we need to prove has 4 of those complex roots. So we're kind of given the hint here. We really need to factor z to the 6 minus 1 into 2 components, one with the bit that we're told and another being the other factor. If we can then find the roots of that other factor, then whatever's left must be the roots of this factor here. So if I just write out for part A, we're looking at z to the 6 minus 1 equals 0. We know that that will have 6 roots. We're told also that, or we want to prove that z to the 4 plus z squared plus 1 equals 0 has the roots w squared, w to the 4, and w to the 5. So we need to factor this. And I think the challenge here is working out, well, how do you factor it such that this will be one of the factors? And I think perhaps trial and error is often the way to go, but actually you can make a pretty good guess because you know the other factor needs to have a 2 in it. It needs to be z squared so that you can get to the 6. And you're going to want to have a minus 1 to get rid of all of these lower factors. So if I was to write, say, z squared minus 1 times z to the 4 plus z squared plus 1, and say, well, what does that expand to? Is it z to the 6 minus 1? Then we've got our factors. So it takes a bit of practice to get good at this, but once you've seen enough of these questions, it does become quite intuitive. But just to expand this, z squared times z to the 4, we'll get z to the 6 plus z to the 4 plus z squared minus z to the 4 minus z squared minus 1. These all cancel and we're left with z to the 6 minus 1 as we need. So therefore, the first conclusion we can make is that the roots of z to the 6 minus 1 equals 0 will include the roots of z squared minus 1 equals 0 and z to the 4 plus z squared plus 1 equals 0. So, if we can find all of these roots, and then find these roots, whatever's left must be these roots. And if those happen to be these, then we've performed our proof. So in terms of finding all of the roots of z to the 6 minus 1, I think the steps to follow would be first to let z equals cis theta. That's just a shorthand. Hopefully you're familiar with cos theta plus I sine theta. We know there's a general result that says cis of 2 pi times k is equal to 1, where k is an integer. And what that's really saying is that the cos 2 pi plus I sine 2 pi will simplify to 1, and that's going to be true for every multiple of 2 pi because of the cyclical nature of cos and sine. The other thing we can say is that z to the 6, if that's z to the 6 would be cis of 6 theta, and that's using de Moivre's theorem. So putting that all together, we can say z to the 6 minus 1 is equal to 0 when z to the 6 is equal to 1. You just bring in the 1 over, which means cis of 6 theta is equal to 1, since z to the 6 is cis 6 theta. And that also means, well, we also know that cis of 2 pi k is equal to 1. So we can equate these and solve for k. So we'll get 6 theta equals 2 pi k. So theta equals pi on 3 times k. And we know we're concerned with theta between negative pi and pi. That's kind of the complete cycle of the Argand diagram, where we've got equality at pi. So therefore, what we really have is negative pi is less than pi on 3k, which is less than or equal to pi. The pi's all cancel, and you bring the 3 up and you get k is between 3 and negative 3 and positive 3. And since k is an integer, we can say that means k is equal to, there's no equality here, so we'd say negative 2, negative 1, 0, 1, 2, 3. You can count those up to check. 1, 2, 3, 4, 5, 6. There needs to be 6 solutions. So those are our 6 values of k. So what I might do is just turn over, but now we can write the values of theta. So we'll have theta is equal, well, we know theta from before was pi on 3k. Therefore, theta will equal, and remembering we've got k is equal to negative 2, negative 1, 0, 1, 2, 3. We'll have theta equals negative 2 pi on 3. Theta will be negative pi on 3. 0, pi on 3. 2 pi on 3. And then 3 pi on 3, or pi. And remembering that w was defined as the smallest positive argument, knowing that that's w, we then get w squared, w cubed, and we loop back around, w to the 4, w to the 5, and w to the 6. And it's probably going to be helpful to draw this up on a Argand diagram, just to make it really clear. So if we've got our real and imaginary planes, I'll just draw 1, 1, negative 1, and negative 1. So we'll just draw up a unit circle. So w will be pi on 3, or 180 on 3 is 60. So if this is 90 degrees, it's about 2/3 of the way through. That's going to be w. w2 will be 2 pi on 3. It's going to be about there. That's w squared. W cubed will be exactly pi. Then you kind of know that the rest will be the complex conjugates. So diagrammatically we'll get w, so that's w3, w to the 4, w to the 5, and then finally w to the 6, with an argument of 0 basically being on the real axis. So those are all the 6 complex roots of unity for z to the 6 minus 1 equals 0. And now what we can do is go, well, if we can pinpoint the roots of z squared minus 1 equals 0, whatever's left will be the roots of z to the 4 plus z squared plus 1. So this is fairly easy. You just, z squared will be equal to 1, so z will be equal to positive or minus 1. So that's going to be W6 and W3. So that means what's left, W squared, W to the 4 and W to the 5 are the roots of the other factor. So therefore, roots of z to the 4 plus z squared plus 1 equals 0 are W squared, W to the 4 and W to the 5. And that's what we were required to show. So that's part A done. Part B asks us to find a quadratic with roots alpha and beta, where alpha is equal to W. I'll just have to check. Alpha was W and W plus W to the 5, and beta was W squared plus W to the 4. So basically, finding a quadratic with certain roots, basically we know the quadratic formula is ax squared plus bx plus c, and we know that if the roots are alpha and beta, there's these general results. Alpha plus beta will be equal to negative b on a, and alpha beta will be equal to c on a. That's kind of something you would have hopefully learned quite a while ago. So really, if we can find what alpha and beta are, we should be able to pinpoint this quadratic. So alpha is equal to w plus w to the 5, and remembering w will be pi on 3, so that's going to be cos pi on 3 plus I sine pi on 3. And then w to the 5, the argument is negative pi on 3, so plus cos negative pi on 3 plus I sine negative pi on 3. And then this can actually be written as cos pi on 3 plus I sine pi on 3 plus cos pi on 3 minus I sine pi on 3. And now I'm just using the result cos of negative x equals cos of x, and sine of negative x equals negative sine of x. Rarely handy identities that always become useful in these kind of calculations. So these will cancel, so we'll get 2 times cos pi on 3. Now cos pi on 3 is a half, but even if you don't commit that to memory, you could just 180 divided by 360. The cos of that is a half. So 2 times a half is 1. So that's alpha. If we look at beta, equal to w squared plus w to the 4. So that's going to be cos of so w2, 2 pi on 3. Plus I sine 2 pi on 3 plus cos of negative 2 pi on 3 plus I sine negative 2 pi on 3. And using the exact same approach, we're going to eventually get 2 times cos 2 pi on 3. And now cos 2 pi on 3, it's going to be negative a half, but just to check, you could say 2 times 180 divided by 3. Cos of that is negative a half, so this will become negative 1. So what quadratic has roots 1 and negative 1? Well, you could probably guess it's going to be x squared minus 1 equals 0. But even if you couldn't guess that, you could use these results. So you could kind of go the long way if you wanted. Alpha plus beta, so 1 minus 1 is equal to negative b on a. So that's just going to give you b is equal to 0. And -1 times 1, or alpha times beta 1 times -1 is equal to C on A. Therefore, C is equal to -A. So you kind of get ax squared, so b is 0, so there'd be no bx, plus c, but c is -a, so minus a is equal to 0, a x squared minus 1 equals 0. The a divides out, you end up with x squared minus 1 equals 0. So you still get there even if you take the long way, but that is the quadratic with these two solutions. So there you have it. I think that's how to tackle that question. I think part A, I think it's the key is getting good at this factorization, and from there working through the steps to work out all the solutions. I always find plotting on an Argand diagram can help, and then from there it should become really clear what's going on. And then part B was just about really just remembering what W and all the powers of W really are, putting in their arguments and being able to get to something quite simple in the end. So hopefully that's all made sense and you found that helpful. And tick boom.